Now, we were examining operational amplifier usage in practice, and we gave some examples. That's the fourth one, and it is called difference amplifier. Let me write the name here. Difference amplifier. So what it does, so the output is going to be something, coefficient here, VA over VS. So these two is independent voltage sources. The voltage difference between those two voltages, multiply it with a coefficient, and you get the output. So that is the difference. So this is the amplifying factor, and that's the output. So we are claiming that this circuit does something like that. That means analyzing the circuit, say whether it does it or not. So in this analyze, we do not need to use node voltage method, mesh current method, the full version of it. Why we don't need that? Because we are going to calculate only one voltage within this circuit. So we don't use the whole method. But what we do need is the definition relation of this ideal operation amplifier, which is Vp minus Vn is equal to 0, almost 0, let's say. Ip equal In is equal almost 0. What does this mean? These two are node voltages. Node voltages, that means that is N terminal, negative terminal of the operational amplifier, the voltage between this and ground. So that is ground. And this Vp is the voltage between this node and the ground, which is also the same as the voltage of Rb. So node voltage, that's why we gave an explanation. We need to give an explanation for that. But the difference between those two voltages gives me the voltage between these two terminals. It says here this is equal to 0. That means this is almost short circuited. Voltage is 0, it means short circuit. So what we are going to do, and we are going to write a Kirchhoff current law for this node. Kirchhoff current law for a node, we need to have the current reference for each element in order to write this. So I mark these current references for all these 4 resistors. So in this equation, in this Kirchhoff current law equations, I am going to have this current plus this current. But on the other hand, I know that this current is equal to 0 since In is equal to 0. So I am not going to write this term in the equation. So that is I minus IRS minus IRF is equal to 0. Why they are minus? Because both of the currents coming towards the node, that's why I put the minus sign in front of it. So this equation is not directly related with that equation. So I've got to transfer these currents to the voltages. How I do it? By using the node voltages. I know this current here, resistor current, and I can write the voltage of this resistor in terms of node voltages under the condition that we calculated this node voltage. So if you find this node voltage which is Vs minus this node voltage over Rs gives you that current. Similarly, I need this node voltage in order to rate this current in terms of voltages. So we need to calculate this node voltage. How I'm going to calculate it? I know this node voltage is the same as this node voltage. Why is that? If you use the definition relation, that voltage is 0, so that voltage comes to here. So this node voltage is the same as this node voltage. Let me mark it in green here. So I need to calculate this node voltage. How am I going to calculate it? If I consider this IP is equal to 0, that means that current is equal to 0. Then that means nothing is connected, or this current equals 0, that is open circuit, that means no connection at all. This results in the serial connection of RA and RB. So if I divide the VA to RA plus RB, which is the equivalent of these serial resistors, then I get that current. That current is so equal to this current. So what I am saying, VA over RA plus RB. That's that current. That current is also equal to this current, since this current is equal to 0. So if I multiply this current with that RB, so I'm going to get this resistor voltage, which is the node voltage of that green. On the other hand, I know that this node voltage is also the same as this red node voltage. So I'm going to multiply this one with RB. So altogether this now is this node voltage. At the same time, it is this node voltage. Then I can write now all these currents in this equation in terms of node voltages. So let me write it, minus RS, this one first, minus RS is Vs, node voltage of this terminal, minus node voltage of this terminal, which is RB over RA plus RB times VA over RS gives me this IRS current, that current. So this is, let me, I can say that is also this. Let me write now minus RISF, so make it different color. So I'm writing this now, minus, so this current is this node voltage V0 minus this node voltage, which is RB over RA plus RB times VA over RF. That's resistance. So I found this current. So when you, so then this current is this current. So when we add those two and organize it, we end up this formula that I'm going to write it. V0 is equal RB times RS plus RF over RS, RA, RB, VA minus RF over RS, VS. So if you write this and organize it in terms of V0, so you end up with this. So if you put this in RF parentheses, V0 is equal RF 1 plus RS over RF. And if I put this RB parenthesis, 1 plus RA over RB times VA minus RF over RS VS. Now we are saying if we choose this ratio RS over RF is equal RA over RB ratio. So that means this and this. If we choose them equal, so then this disappears, this disappears, this disappears, this disappears. What is left is this, isn't it? V0 RF over RS VA minus VS. That is the results that we were expecting. So then we can say that the voltage difference is multiplied with this coefficient. So by choosing the values RF and RS, you can arrange the amplifying coefficient, then you get the output. So difference amplifier in practice has a strong meaning. When I will explain it to you now. Assume that you've got some mechanical, hydraulic, or pneumatic systems. Any quantity measurement is not easy in these systems. If we transfer these quantities to electrical quantities, that means sensors. By using the sensors, we could do that. So you can use a reference voltage and assume that this voltage is the sensor's output voltage. That means the quantity that you are measuring is transferred to this one. So this difference is going to be a very small difference, volt difference. So you've got to increase that in order to make it measurable in electrical sense, I mean. So you are going to measure this voltage. Once you measure that voltage, then that means you found this difference, and according to the sensor properties, you can transfer this voltage back to the original physical quantity that you are trying to measure. Therefore, we use the difference amplifiers quite often in practice. So this is a good application of an operational amplifier. So that is the end of this video.